So this video needs to be used like side by side or in conjunction with the next video. All right, here we're going to show something, but in the next video, we're kind of actually going to apply it. All right. Now, we all know that sine and cosine are defined like this. What I have here is what they call the unit circle. All right, so this is what they would call the unit circle definition for sine and cosine. And this is going to be way more efficient, way better, more useful for our trig functions. All right, all of our trig functions are actually, you can find them in the unit circle here. Now, because it's a unit circle, we say that it has a radius of 1. So all throughout this, the radius is going to be 1. So let's go ahead and identify these 4 points on the end here. So since this is on the regular XY coordinate grid, we know the value at this spot is going to be 1 for X and 0 for Y. So 1, 0. Likewise, this one is 0 to the left and right and positive 1. Now, as you go 180 degrees over here, you're going to get negative 1 for X and still 0 for the Y. And down here, you're going to get 0 for X again, negative 1 for Y. Okay, I guess while I'm here, I'll give you the equation. Here's the equation for the unit circle. We're not really going to use this, but since we've talked about circles in the past, might as well mention it. So it's like, translated 0 to the left and right, the center is 0, 0, and it has a radius of 1. So now you might be asking, how is this going to help us with trig functions? Isn't trig functions about triangles? Well, yes, it is. And it still is, but we're gonna be thinking about these triangles differently. So like right now, you can only take the sine and cosine and tangent for angles that are, in between. They have to be in between 0 and 90. Or 0 and pi over 2. All right, that's the only way that you can evaluate trig functions. That's the only way they have meaning, because right now they only apply to these right triangles. Okay, but there are way more angles that exist. All right, there's a 360-degree angle. There's a 400-degree angle. There's lots of them, and trigonometry applies to those as well. So to start out, what we're going to do is I'm just going to focus on the first quadrant here, and I'm just going to draw a random point. So I'll do that one right there. So that point, it has an X and a Y. All right, it has some value. I'm going to label it as like A, comma, B. And I'm going to draw my radius that meets up at that point. So there's 2 things to notice here. First off, if we're thinking of it in standard position, this this segment that I drew has some angle. We don't know what the angle is. We're just going to call it theta. The other thing to notice is that this radius, this segment, because we're dealing with the unit circle, we know that this has a length of 1. So what we do here is going to apply to multiple radii, all of them actually. All right. And the reason why is because they're all going to be similar to this one. All right, like all circles are similar to each other, if that makes sense. Next, I'm going to go ahead and drop a little altitude. So it's going to meet my x-axis. It's going to meet right here at a 90-degree angle. And so this is where your right triangle trigonometry comes in handy. So notice this little distance right here, that distance there, because point AB is right here, this just must be that A value, that horizontal distance. We're going to call that A. And this up and down distance, right, the up and down is going to be B. But there's more than one way to think of it. Depending on where A and B are, all this stuff would change. Of course, it would still be a right triangle, but we're gonna think of these numbers differently. We're not even going to use the Pythagorean theorem, really. Instead of thinking of it as A and B, what I want you to look at is sine and cosine of this angle. All right, this is where the insight comes, okay? If we look at cosine of theta, remember cosine's adjacent over hypotenuse. So the adjacent side for this theta is going to be this segment right here. All right, because we're looking at this right triangle. So that's A. I guess we could just call it, A over, and then our hypotenuse is, this hypotenuse. Well, that's 1. So what this boils down to is that cosine of theta is equal to A. Well, that's kind of handy. That's neat. So cosine of theta actually represents the horizontal distance for our point on the circle. All right, let's do the same thing for sine real quick. Sine theta is going to be opposite over hypotenuse. Well, the side that's opposite angle theta is going to be this B. So we get B over the hypotenuse, which is 1 again. And then this is going to boil down to just be sine of theta equals B. Well, now this is really nice because what I can do is just substitute A and B for cosine and sine. And so what we get is we get this other way of thinking about sine and cosine. All right. So when you're dealing with circles, or the unit circle in this case, all right, this is a point. When you're dealing with unit circles, no matter where you are on this circle, every point can be thought of as sines and cosines. Cosine is going to be like your x direction, how much to the left and right the point is on the circle. And the up and down is going to be represented by your sine. And so this is going to be true for quite a while. We're going to be focused on this for quite a while. Cosine is going to act kind of like our x's, and sine is going to act like our y values. All right.